Did you guys need to wear Under Armour in my game today?
Hey.
No.
Alright. Ladies and gentlemen, class recording has started. So, on Friday, we began our discussion of mechanics, which is the study of motion. It was like our quote-unquote first real physics unit. So we sort of used the context of you spotting the ice cream truck and trying to relay that information to your friend to introduce some of the ideas. And we said there's some certain things that we want to know about the motion of an object in order to accurately describe it to somebody else. So what are some of the things that we discussed, some of the questions that we want answered regarding the motion of that object? Good.
Where is the object?
Where is that object?
When you saw it.
When you saw it. What else?
How fast it's going?
How fast it's going, or what is it doing right now, right? And then
What direction?
what direction? We'll get into that a little bit more, right? And then there's one other thing. What will it be doing? Like, is it changing what it's doing? Okay. If we answer these 4 questions, that's a lot of what mechanics is about. So with that being said, we started off at the beginning. We talked about the position of an object. And we said that an important part of describing the position of the object is setting some context, right? We call that context our frame of reference. That if you're going to accurately describe the position of an object, you first have to describe, okay, where am I describing it from? And I think we kind of use the example of, if I give you a treasure map to work with, right, what do I first have to tell you in order for you to successfully use the treasure map? Where to start. If I don't tell you where to start, all the rest of those directions mean absolutely nothing. So we have to have ourselves a reference point. And then along with that reference point comes a directional system, which we'll get into a little bit more later on. Okay. So we said that this is great, that describing the position of an object is fine, but not everything stays where it currently is. Sometimes things start moving around. And so we have to describe that motion, or what happens as it moves around. We talked about the idea of displacement. Displacement being defined as the change in position relative to a reference point. And I think we concluded class with the picture of this gecko, yes?
Yeah.
Okay.
And we're like, oh, it has to be in suspense.
Right. So we take a look at this gecko. First, we use this notation, right, to represent the displacement of an object, delta x, because if our definition of displacement is the change in position, if we want to know the change in something, what do we need to know? We need to know where it starts and where it ends, right? So the displacement of an object depends on where it starts initially, its initial position, and then its final position. This picture, representing a meter stick, used to measure this gecko's motion. And so we said that, as he's moving along horizontally in this picture, a lot of times we'll refer to that as the x-axis, right, from math class, blah, blah, blah. So the change in position, delta x, right, the delta representing change, final minus initial. Where does it end versus where does it start? We got some measurements, boom, we got that this gecko's displacement was 61 centimeters. Good there? But then, I left you with the cliffhanger of, well, what happens if we have this? First, is this different than the previous motion? Yeah, right? If you're trying to describe the ice cream truck to your friend, you call up your friend and you say, hey, I just saw the ice cream truck in front of my house, is it important for you then to tell your friend which way it was heading? If they want to try and get to the ice cream truck, they got to know which way it's going. So the fact that this gecko is going in a different direction than the other gecko, or just later, probably the same gecko, but whatever. Okay. But if this is going in a different direction than it was previously, we have to reflect that. Starting off, we're still going to call it displacement. So we're still looking at delta x, the change in position. And we said that if we want calculate delta x, we need to know two things. What are the two things we need to know? Where it started and where it ended, right? So we still go x final minus x initial. Good there? That being said, we start looking up at our picture and we start plugging in numbers. So what is the final position of this gecko as indicated by this picture? 14, right? You know, our interpretation of that can change just depending on how we go, right? We'll call it 14, okay? Minus the initial position of this gecko, which is 79, 78, whatever, okay? So 79 centimeters. We do that math and we end up with what? Negative
65.
negative 65 centimeters. Okay? So everyone see that? You good with that? Okay. Obviously, there's one big difference between this answer and then the previous answer that we looked at before, and that's the what? That's the negative sign, okay? And that's important because displacement is the first example that we run into of something called a vector quantity, okay? Displacement is our example of a vector quantity. Vector quantities will answer two questions for us. Vector quantities will tell us both magnitude and direction.
Sorry.
Is that okay?
It's like that guy from Despicable Me.
Exactly. You're the first person. You're the first person, please.
Sorry.
It's obviously not surprising to me, but so everyone see where
Magnitude. Oh yeah, that's where it's from.
in Despicable Me. You ever see Despicable Me? The bad guy's name in Despicable Me is Vector because he has direction and magnitude. So
Oh yeah. That's how he says it.
anyway, when we talk about vector quantities, two things that a vector quantity will tell us. They will tell us how much or how big something is, but they will also tell us which way that object is going. Now, that being the case, for the direction part, you need to distinguish one way from the other. If we go back to this gecko situation, right? This gecko is limited to what we call one dimension, right? One dimension is a straight line. And on a straight line, you've only got two options, right? Which way can you go?
Left or right?
Left or right, or this way or that way. So, we can use positive and negative to distinguish those two directions. Because we've only got two options. Just like on a number line. You got a middle point, right? And then you got a positive side and you got a negative side. Okay? That being the case, though, once you start moving into more dimensions, right? When we get into math class, we talk about like 2 dimensions, right? You got an x-axis and a y-axis. And then in real life, you get into 3 dimensions, where you have an x, a y, and a z-axis. And how we distinguish direction there changes. You can't just go positive and negative because there's more than 2 choices. We're not going to do that in this class. That's what we do in physics. But we're going to introduce these concepts of direction here and then apply them a little bit later on when you get to physics. So, vector quantity, magnitude, and direction. Okay? That being the case, let's go here. Okay? Here's a little story, and you have a copy of this story down at the bottom of your page, and then a picture that goes along with this story. So it says, a man starts out from his house and drives east 50 kilometers. After an hour, his car runs out of gas. He walks the next 5 kilometers east until he reaches a gas station. He sits at the gas station for 30 minutes to fill the gas can and get something cold to drink. He then walks back west for 3 kilometers, but a kindly stranger gives him a ride the remaining 2 kilometers to get back to his car. When he finally reaches his car, he drives back west 50 kilometers to arrive back at his house.
I said after that instead of after an hour. So
Sorry,
does
that's
that
fine.
matter?
No, it doesn't matter. Because here we're just talking about where, right? We're not talking about when just yet. Okay, with that being said, if you flip it over to the back of that page, you will see that there are 4 questions. 4 questions that relate to this story. So, why don't you take 2 minutes, talk to the people around you, and see if you guys can answer those 4 questions. Ready? Go.
Is there a reference point his house? The RT? What? I mean, yeah. The reference point is his house. So would it be 50 kilometers? And then the man he arrived at the gas station. Would be 50 from his car, from the house. For the second one is from his house or from his car. I think it would be his house. So 55 kilometers. And then when the man's displacement, when the current stranger picks up, 52? 53? Wait, 52, right? Because he goes 50 and then it starts block 2. Yeah, 52. And the last one is what man for his entire trip.
Alright, one more minute. One more minute.
It's separation between the change in position relative to the reference. You go, Katie. The change in position for the reference point, but they're not changed. If they get back to the original point, then is it just 0?
He just drives 50 and then.
Perhaps because his car ran out of gas, he missed whatever it was that he was going to do. So then he just went because he missed whatever it was that he was supposed to do. I was going to include that in the description, but then figured some smart aleck would bring that up in class.
It's okay, because then you found $5.
Wow.
That's how you end a pointless story. And then I found $5.
Alright, so let's discuss. So the man's displacement, we said displacement depends on 2 things. Displacement depends on what? Initial position and final position. In relation to what though, Jeff? Did you say reference point? But it's his initial position and his final position in relation to his reference point, right? Joe, what's probably the reference point in this problem? Probably the house, right? Okay, so with that being said, what would be the man's displacement when his car runs out of gas? 50 kilometers east. Because we said displacement is a vector quantity. Is which direction he goes important to describing his trip?
Yes.
Absolutely. Okay. So the second question, what is the man's displacement when he arrives at the gas station? If we still keep the reference point being the house, which we should to make consistent with this situation, it would be what? 55 kilometers east. Okay. Good there? Okay. Now, here's where things start getting interesting, right? What is the man's displacement when the kindly stranger picks him up? At 52 kilometers east. He went back, he went back west, but where is he in relation to the reference point? He's still on the east side of the reference point. Even though he went back towards the west, his displacement would still be 52 kilometers east. And then the last question, what is the man's displacement for his entire trip?
110 kilometers.
0. Okay? That's the next problem then. Okay? So, the man's displacement for his entire trip is 0 kilometers because what do you know about his starting point and his ending point? Same spot. Okay? Now, does displacement do a good idea of describing what happened to an object in motion?
No.
Sometimes, but sometimes not. if you asked the guy and you said, hey, what was your displacement this afternoon? He said, oh, 0 kilometers. Is that a good description of what happened to him during the afternoon? Not really, right? So sometimes displacement is important. Other times we need a little bit more different information.
I'm gonna ask you that.
And that gets us to
What was your displacement?
the idea of distance traveled. So, distance traveled, by definition, the total length of the trip taken between a starting point and an ending point. The important part being there, the total length of the trip. Go for it.
The distance traveled for the man is from T0.
We'll talk about that in just a second. All right, so that being the case, then this is the definition of distance traveled. Here's those 4 questions again, except instead of asking you for the displacement of the man, it's asking you for distance traveled for the man. So why don't we take a minute, discuss those 4 questions with the people around you, come up with some answers for those, and then we'll discuss together as a group. Go.
Is it an example of a scalar quantity?
The second one is
How is that
55. The third one,
It says scalar quantity.
It's not.
110. 110.
Good job, Katie. I can't believe nobody else got those from Despicable Me. Have you seen that movie?
Is that an animated movie?
There's the one
No,
with
there's
like
real
the
life
yellow
yellow
like corn pop.
Oh no, I didn't know they were real. You know, for
You've never seen it?
They're called Minions. I
I'm
think.
still angry at her. She cheated and robbed me of my extra.
Oh my,
No,
on what? She cheated off you?
No. She cheated on a game. She cheated. Whoever your person was like, I don't know the answer. And I was like, oh, I got this, and just broke the whole thing. No, Barbara, go take your turn. Oh, this is all being recorded.
That's what I was gonna keep letting you rant. Yeah, because
So basically, Bara cheats. Don't play cards with her.
All right, so let's get started
your
here.
cards where I can see them. It's not.
So the
called
first
cheating.
question says,
It's called being stupid on your behalf.
first question says, what is the man's distance traveled when his car runs out of gas? So how far has he gone until his car runs out of gas?
50 kilometers.
50 kilometers. Second question, what's his distance traveled when he gets to the gas station? 55 kilometers. Now, the first 2 questions, we don't really see much of a difference, right? Because what hasn't happened yet? He hasn't changed his direction. But starting after beginning, when he leaves the gas station, now he's traveling back in the opposite direction. Now we see a difference between distance traveled and displacement. So what is his distance traveled once the kindly stranger picks him up?
5'8".
58 kilometers. And then the distance traveled for his entire trip would be 110 kilometers. Okay? So, distance traveled. Distance traveled is an example of a scalar quantity. Okay?
Nice one, Nicole.
Scalar quantities will only tell you magnitude. And we said that magnitude is only a matter of how much or how big. Distance traveled is a scalar quantity. It tells you how far you went, but it doesn't make any distinction about the direction that you go in. Go ahead, Farrell. Because it's 50 his car runs out, 5 more to get to the gas station, 5 to get back to his car, and then another 50 to get back to his house. Okay? All right. So other scalar quantities. Most of the things that we have run into already this year are scalar quantities. Things like mass and temperature and time. These don't have direction, but that doesn't mean they're not important. So, which one's better? Displacement or distance traveled?
Together.
It depends what you want to know, right? For example, let's go back to our situation of you and the ice cream truck. So, alright, there's your house on the corner, right? And you hear the ice cream truck right when it passes the front of your house, but you're too slow to get outside and stop it, right?
You probably should have done ice cream.
I just meant you didn't get out fast enough. Not that your physical condition
Maybe you were in
prevented
the
you from getting out
bathroom.
fast enough.
Maybe you were in the bathroom.
That makes sense.
Maybe that's your exercise regimen, chasing the ice cream truck. But, so this ice cream truck, right, takes a right-hand turn. It goes down this street, but this street is a cul-de-sac, right? And it goes around the edge of the cul-de-sac, right? And eventually it's going to end up right here. Do you care how long the cul-de-sac is or how many people it stops at on the street? But eventually, you know that that ice cream truck is going to end up right there. All you're concerned about is you knew it was in front of your house at one point in time, and eventually it's going to be over here again. Okay? You only care about the displacement of the ice cream truck. But the guy who drives the ice cream truck has to know that he's gone down here and went all the way around the cul-de-sac and then back up here, because eventually he's going to have to stop and get gas, right? Yeah. For the ice cream truck, distance traveled is important. Okay? If we talk about you during your day began this morning when your alarm clock went off or when your mom woke you up. Where were you at that point in time? You're in your bed, right? Where are you eventually going to end back up today? In your bed. Does that tell you, most likely, some of you might crash on the couch or whatever, right? But does that tell an accurate picture of what you did today? Not really, right? But that is where you started and where you ended up.
That's a picture of my day.
All right. That being the case, we've now taken care of where is that object. Okay. So the next question we said we want to know is what? What is it doing? Okay, so we know where it is, but it's important that we know what it's doing if we want to accurately describe that situation. So the next slide that we come across is speed. Okay? So, speed is a definition, or by definition, is the rate at which distance is traveled. Speed is the rate at which distance is traveled. Now, something you've probably come across before, maybe in math class, maybe in math class. When we talk about something, we describe it as a rate. There is something that we are including in that description. If we describe something as a rate, what factor is automatically included?
It's something you just eat. What are you doing?
Except it's not that. But the one factor, Kitty, taking that into account, the one factor is what? This is the distance part. What else has to be included here? Time. Okay? Whenever, I heard it.
It's a
So, whenever we describe something as a rate, there is always a time factor involved there. So, speed is defined as the ratio of the distance an object moves and the time it takes to move that distance. Speed is a ratio between the distance an object moves and the time that it takes to move that distance. talked about on Friday. What is the reason why we make graphs out of data?
To show us.
To show what?
Visualize the
A trend and
To
patterns.
show trends and patterns. To represent the relationships. Same thing is true here, right? Yeah, this is a great description of what speed is. But every time we talk about speed, we don't want to have to throw this out, right? So how do we represent that relationship? Looks like this, right? A ratio between the distance an object travels and the time it takes that object to travel. Right? Speed is equal to d over t, distance over time.
Is that we prefer the formula?
Yeah,
Okay.
the formula. Now, can we measure speed with one measurement? You got to measure two things. You got to measure how far does it go and how long does it take to go that far, right? So the unit can't be a single unit. The unit is a derived unit, right? So, right, meters per second or meters over seconds, because you got to measure both of them if you're going to describe the speed of the object. Good there? So let's go here. And let's take a look at this picture, right? This picture representing a girl running a race. If we want to calculate this girl's speed, we have to know two things, right? What do we have to know?
How far she's running and how long it took her.
We need to know how far did she go, distance traveled, and how long did it take her to go that far, right? Now, these stopwatches up at the top, they reflect the time at a certain location, right? So this time representing her time at that location. So, based on this information that we have, what is the distance that she has traveled? 50 meters, right? That goes there. And then how long has it taken her to travel 50 meters?
35 seconds. 35 minutes.
This stopwatch goes with that location. Okay? So, does that make sense?
You know what? We never had to use second stopwatches. They look like pocket watches.
Good afternoon, everyone. Finding order for two quick announcements. Attention SAD members who signed up for tonight's dinner and play, please come to the library at 6 p.m. where dinner will be served before the presentation at 7. So SAD members who signed up for tonight's dinner and play, please be in our library at 6 p.m. Our other announcement, please join Chipotle Mexican Grill Monday the 15th, that's tonight, from 4 to 8 p.m. 50% of the proceeds from sales tonight between 4 p.m. and 8 p.m. will be donated to a service organization providing medical service to developing nations and nations in turmoil. So looking at some of the services they provide to orphans and medical care, particularly in the Mideast and in North Africa, please stop out and support that cause by having dinner at Chipotle. All right? Everybody have a great afternoon. We'll see you tomorrow.
All right. Hey. First of all, that doesn't mean class is over. You all know that.
Yeah, we do.
So if this is on the test, it's still going to be on the test, all right? So,
What you doing?
is that the answer to this problem? No, right? Emily, what do we have to do? Now, there aren't a whole lot of good measurements of significant digits here in this picture, but how many significant digits would 50 have? 1. How many significant digits would 6 have? 1. So that means we're doing a division problem, so we should round this answer to 1 significant digits. Division's always the least number. Okay? Now, to finish this off, is that an accurate description of this girl's motion?
No, because she can't keep that pace.
Well, she could, but,
No.
right? If you're trying to describe what the ice cream truck is doing, you call up your friend and say, hey, I found the ice cream truck. I saw the ice cream truck right in front of my house. What information would your friend probably want to know?
How fast is it going?
Where is it going, right? This is telling you how fast, but not necessarily what. Where? Which way? So there has to be a vector factor version of this number. That's where we pick it up tomorrow or on Thursday. Okay?